a cricket situation. So you've got a cricket ball up here, attached, I assume, to a hand. I hope, otherwise like some ghost cricket ball or something. And Glenn the fast bowler. Let's draw Glenn, shall we? How do you hold your?
He needs a taller neck. He needs a taller neck.
This is.
Oh wow!
This is the. Yeah, I don't know.
That's amazing.
But anyway, okay.
Boring.
This is the greatest diagram of all time. Okay, 2.4. Yeah, that's probably. He's pretty tall. Anyway, so the picture is he has the ball and he's about to release it. Okay. He throws about 144 kilometers per hour, which is actually way slower than he bowls. I think they just do that to make the numbers neat. He's close to like 150 plus. Actually, well, he's close to 0 now because he's retired. But anyway. And he throws it down at a 7-degree angle of depression. Okay, so you can see it there off the tangent. So what's being asked? A few things. Okay, so firstly, we're asked to prove some equations for, I think for x dot, no, for x and for y. Okay, so as usual with all projectile motion questions, we start with acceleration. Okay, so horizontal acceleration, as you know, it's 0. And we have to build from here by integration all the way up to the x function. Okay, now it's unfortunately a little bit laborious. You really must include all 4 constants because you integrate 4 times. Okay, please don't do shortcuts there. Be rigorous in the way that you do it. So I actually write, just to remind myself to actually put the constants in, that x dot is the integral of x double dot with respect to time. Okay, that's an unnecessary step. It really is, but I put it in just for myself. So since it's just 0, right, it's going to be a constant. And if I'm going to evaluate that constant, I'm going to need to know, okay, what is the initial motion over time? Okay, so therefore, this is where you start to bring in your rectangle. Okay, so it's going downwards, right? So I'm going to draw it sort of like this. Okay, I've got 144 kilometers per hour, but they ask for the resultant equations in meters per second. Okay, so just watch for that. Therefore, I'm going to have to convert 144 kilometers per hour is 144,000 meters per 3,600 seconds, right? So that's just my conversion, okay? Once you divide through, I think you get 40. Okay? Now, what else have I got here? This is 7 degrees. That's my alpha, my initial angle, okay? And so because I'm thinking about horizontal and vertical, right? X dot, this part you can quote. X dot is V cos alpha, right? V cos alpha. So there's my V, 40, and my alpha is 7, right? So 40 cos 7. While I'm at it on the diagram, I might as well do y dot, and it's only different by the function. So it's going to be 40 sine 7. At least it's almost 40 sine 7. What am I missing? It's just got to be negative, okay? Please watch out for your signs. I mean, the fact that I've drawn this diagram downwards ought to clue you in, okay? But it's decreasing, okay? It's going closer towards the origin, the ground, rather. Okay, so when t equals 0, x dot's equal to this. Actually, when t is anything you like, x dot is equal to this because horizontal velocity is a constant. So therefore, I can say c1 is going to be equal to that constant. Okay, so here's my acceleration for any value of time. Integrate another time. And you slap your t in there, plus your second constant. We're starting at 0, okay? So therefore, this constant, as it usually does, turns out to be 0, because it's a bit silly to sort of define your starting point as something non-zero. Okay, so C2 is equal to 0. Therefore, here's the first step that you get, first result rather, that you get asked to show. Is that right on the question 12? Yeah, does that look right? Thumbs up? Okay. Alright, move on to y dot. Okay, so, sorry, y actually. Will I have enough room? Not quite, but I'll try and squeeze in. Start from acceleration. And I think they specify 10 for gravity. So we've got minus 10 here. So integrating once, I'm going to get minus 10t plus my constant. Okay, there's my value for what y dot is equal to initially, right? So when t equals 0, y dot is equal to v sine alpha. Okay, so therefore 40 sine 7 is equal to 0 plus 0. Okay, sorry, minus. Caught myself, okay? So therefore, y dot minus 10t minus 40 sine 7. Is that right? Okay, integrate again to get up to the displacement function, at least for y anyway. So y is the integral of y dot dt. So minus 10t turns into the familiar minus 5t squared minus 40t sine 7 plus my constant. Sorry, I called this constant 1. That's a bit naughty, isn't it? I think that's up to 3. And here's constant 4. Now here's where the question gets it wrong. They call this point the origin, but quite obviously it's not the origin, okay? So therefore, when t equals 0, according to this diagram, y is 2.4. Now by the way, we could just as easily have defined this as the origin, and later on when we're trying to work out this spot, it would be minus 2.4. It doesn't matter, okay? Here we're going to have y be equal to 2.4. So 2.4 is equal to minus 5, 0 squared. Okay, so there is my C4, right? That's the value I'm actually going to slap in. So therefore, my actual displacement function is minus 5t squared minus that plus my constant. Is that what I wanted to show? Happy so far? Right, now